Tonight, we're going to take a journey to the strangest and most terrifying planets ever discovered, real worlds. Worlds with names and coordinates, worlds that astronomers have measured and weighed and watched. A planet where the wind blows at 8,000 kilometers per hour and the rain is made of molten glass. A planet blacker than coal, so dark it swallows almost every particle of light that touches it. A planet where iron evaporates into the sky on one side and falls as burning metal rain on the other. You probably think you know what a planet is. Something round, something solid or gaseous, something that circles a star the way Earth circles the sun, quietly, predictably, forever. But here's the thing most people don't realize. In the last 30 years, we have discovered more than 6,000 planets beyond our solar system, and almost none of them are anything like the calm, orderly worlds we imagined. What we found out there isn't just unfamiliar, it is stranger, more violent and more extreme than almost anything science fiction ever dared to invent. And by the end of tonight, you're going to understand exactly why. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. For almost all of human history, we knew of exactly one planetary system, ours, the Sun, 8 planets, a scattering of moons and comets and asteroids, all turning in the dark like the workings of an enormous, patient clock. Every idea we had about what planets were, how they formed, how they behaved, came from this single example. And our system is, by cosmic standards, remarkably gentle. The planets follow nearly circular orbits. They keep respectful distances from their star. The rocky worlds sit close in, the gas giants farther out. Everything arranged with a tidiness that feels almost deliberate. So when astronomers began to imagine planets around other stars, they imagined something familiar. Other suns with other Jupiters, other Saturns, maybe other Earths. Different in detail perhaps, but built on the same quiet blueprint. It was a reasonable assumption. It was also completely wrong. Think about that for a second. Every single planet humanity had ever studied for thousands of years belonged to one system, one data point. Building a theory of planets from our solar system alone was like trying to understand all of humanity by studying one quiet family in one quiet house, on one quiet street. Whatever you concluded would feel complete, and it would be missing almost everything. The first crack in that picture appeared in a place nobody expected, not around a warm yellow star like our sun, but around a corpse. In 1992, two radio astronomers, Alexander Wolszczan and Dale Frail, confirmed the existence of two planets orbiting a dead, collapsed star called a pulsar, more than 2,000 light-years away. We'll return to those planets later tonight because their story is one of the strangest of all. But the important thing is what they represented. The very first planets ever confirmed beyond our solar system were not orbiting a friendly star in a comfortable orbit. They were circling a stellar corpse bathed in radiation in a system that had already died. The universe was trying to tell us something right from the beginning. Planets do not need our permission to be strange. 3 years later, in 1995, astronomers found the first planet orbiting a normal, sun-like star. It was called 51 Pegasi b, and it broke the rules all over again. It was a gas giant, roughly half the mass of Jupiter. But instead of orbiting far from its star the way Jupiter does, it was pressed up almost against the stellar surface, completing an entire orbit, an entire year, in just over 4 days. Astronomers called it a hot Jupiter, and at first, many refused to believe it was real. A giant planet simply wasn't supposed to be able to exist there. The discovery was so important, so completely disruptive to everything we thought we knew, that it eventually earned Michel Mayor and Didier Queloz the Nobel Prize in Physics. 1 planet, 4-day year. And the quiet blueprint of our solar system stopped being a blueprint and became what it had always been, a single example, nothing more. Since then, the floodgates have opened. As of this year, astronomers have confirmed more than 6,200 planets orbiting other stars, spread across more than 4,700 planetary systems. Thousands more candidates are waiting in line to be confirmed. 6,000 worlds, each one a real place, with a real sky, real weather, a real horizon that no human eye has ever seen. And here is the number that should stop you for a moment. Among those 6,000 confirmed worlds, the calm, familiar, Earth-like ones, the ones our imagination kept insisting on, are so rare that we are still not certain we have found even one true twin of our own planet. What we found instead were the monsters. It's worth pausing to appreciate how we even know these worlds exist, because we have never photographed most of them. Not really. Nearly every planet you'll hear about tonight was discovered indirectly through 2 beautifully simple tricks of light and gravity. The first is called the transit method. If a planet's orbit happens to carry it directly between us and its star, the star dims, just slightly, often by less than 1%. A space telescope called Kepler stared at a single patch of sky for years, watching more than 100,000 stars at once, waiting for those tiny rhythmic dips. Each dip, repeating like a heartbeat, was a planet announcing itself. The second trick is called the radial velocity method. A planet doesn't simply orbit its star. Star and planet orbit each other, circling their shared center of mass, which means the planet's gravity tugs its star into a tiny wobble. That wobble stretches and compresses the star's light in a way our instruments can measure with almost unbelievable precision. We can detect a star being pulled back and forth at walking speed from hundreds of light years away. The spacecraft that transformed this from a trickle of discoveries into a flood deserves a moment of its own. The Kepler Space Telescope launched in March of 2009 with a single, almost absurdly patient assignment. Point at one patch of sky near the constellation Cygnus. Watch 150,000 stars in that patch, all of them simultaneously, and do not look away, not for hours, for years. Kepler measured the brightness of those stars over and over. relentlessly, watching for dips of a fraction of 1%. And from that single stare, it discovered thousands of planets, more than every other method and telescope combined at the time. It kept going until its pointing system began to fail. One reaction wheel in 2012, a second in 2013, and even then engineers found a way to balance the crippled spacecraft against the gentle pressure of sunlight itself, like steadying a rowboat against a current, and the mission carried on for years more, discovering hundreds of additional worlds until the fuel finally ran out in 2018. A small telescope, staring at one patch of sky, rewrote our understanding of the entire galaxy. Most of the strange worlds in tonight's journey owe their discovery, directly or indirectly, to that patient, unblinking machine. Imagine that. We are reading the weather on worlds we cannot see by watching starlight flicker and stretch across distances so vast that the light itself has been traveling since before you were born. From those flickers, astronomers can determine a planet's size, its mass, its density, the length of its year, the temperature of its skies, and in some cases the actual chemical composition of its atmosphere. Every fact you will hear tonight was extracted one photon at a time from the light of distant suns. And the picture those photons paint is not a gallery of quiet blue marbles. It is a bestiary, a catalogue of worlds so extreme that astronomers, careful, conservative scientists who measure everything twice, have ended up using words like lava world and iron rain and darker than coal in official scientific publications. So tonight, we're going to visit them, one by one. We'll walk through the strangest weather in the known universe. We'll stand, in our imagination, under skies that would kill us in an instant, on worlds that reject every comfortable assumption we've ever made about what a planet should be. And as we travel, something unexpected is going to happen. With every nightmare world we visit, the planet you are lying on right now, the one holding you up at this very moment, is going to seem less ordinary and more impossible. But we'll come to that. For now, let's start our journey somewhere deceptively beautiful. 64 light-years from your bedroom, there is a planet the color of a deep, perfect ocean. It is the exact blue of a postcard from paradise. And it is one of the most violent places we have ever discovered. The planet is called HD 189733b. The name is just a catalogue number, the 189,733rd entry in a list of stars compiled a century ago, with a small letter B to mark the first planet found in orbit around it. It sits about 64.5 light-years away in the small northern constellation of Vulpecula, the Little Fox. 64 light-years sounds almost neighborly by cosmic standards. But let's translate that. 1 light-year is about 9.5 trillion kilometers. So this planet, one of the closest hot Jupiters we know, and one of the most studied planets in the entire sky, is more than 600 trillion kilometers from where you are lying right now. The light reaching our telescopes from that world tonight left it around 6.5 decades ago. When you look at data from HD 189733b, you are looking at the past. The planet was discovered in 2005, caught in transit across the face of its orange dwarf star, and astronomers realized almost immediately that they had been handed a gift. Because HD 1189733b is so close to us, and because its star is relatively bright, and because the planet crosses that star so deeply and so often, every 2.2 days, it became one of the most observable planets in the entire sky. It has been called a Rosetta Stone for exoplanet science, the world on which technique after technique was tested and proven. Water vapor was identified in its atmosphere. Its temperature was mapped from a distance of 600 trillion kilometers, well enough for scientists to publish a weather map of a world no camera can resolve. When astronomers want to try something new and audacious with an exoplanet, this planet is very often where they try it first, which is exactly how we came to know its color. In 2013, the Hubble Space Telescope managed to do something extraordinary with that ancient light. By watching carefully as the planet slipped behind its star, comparing the light of the system with the planet visible and with the planet hidden, astronomers isolated the light of the planet itself. And from that whisper of reflected starlight, they determined its color. This was the first time in history we had ever directly measured the true, visible color of a planet outside our solar system. And the answer was breathtaking. HD 1189733b is blue, not a dull, grayish blue. A deep, saturated cobalt blue, the blue of Earth's oceans photographed from space, the blue of the planet in every hopeful piece of science fiction art ever painted. If you could see it up close with your own eyes hanging against the black of space, your heart would leap. It looks like home. It is not home. And here's where things get uncomfortable. Earth is blue because of water. Sunlight pours into our oceans. The water swallows the reds and yellows, and what scatters back out into space is that soft, living blue. HD 1189733b has no oceans. It is a gas giant slightly larger than Jupiter, with no surface at all. And its blue comes from something else entirely. Its skies are filled with clouds of silicate particles. Silicates are the mineral family that makes up most rock on Earth, and they are the main ingredient of ordinary glass. On this planet, it is hot enough that rock-forming minerals exist as vapor in the atmosphere, and as that vapor rises and cools, it condenses into tiny droplets. Droplets of molten glass, drifting in the clouds, scattering blue light in all directions. The beautiful ocean blue that makes this world look like paradise is the shine of an atmosphere full of microscopic glass. Now let's talk about the weather, because this is where HD 1189733b earns its place at the start of our journey. The planet orbits its star at about 1/30th of the distance between the Earth and the Sun. Its year, one complete orbit, lasts just over 2 Earth days. Being that close does two things. First, it heats the atmosphere to somewhere around 1,000 degrees Celsius, hot enough to melt aluminum. Second, it almost certainly locks the planet's rotation so that one face points at the star forever, and the other faces permanent night. One hemisphere in endless blinding day. one hemisphere in endless dark, and between them, an atmosphere desperately trying to even out the difference. That desperation becomes wind. When astronomers mapped the movement of the atmosphere, tracking features in the planet's clouds and measuring how its light shifted, they clocked winds of up to 8,690 kilometers per hour. Let that number settle for a moment. 8,690 kilometers per hour. The strongest hurricane gusts ever recorded on Earth are around 300 or 400 kilometers per hour. The great storms of Neptune, the fastest winds in our solar system, reach roughly 2,000. This planet's jet stream moves more than 4 times faster than that, many times the speed of sound, a planetary-scale river of superheated air roaring endlessly from the day side to the night side, carrying the heat of a star across a world that can never turn its face away. And in that wind, the glass flies. Those silicate droplets in the clouds, the ones that give the planet its beautiful blue color, do not fall gently. In a jet stream moving at thousands of kilometers per hour, nothing falls gently. The rain on HD 11897333b, if we can even call it rain, almost certainly moves sideways. Sheets of molten glass hurled horizontally through a 1,000-degree sky at speeds no aircraft ever built could survive. There is no ground for it to strike because a gas giant has no ground, so the glass simply falls and flies and evaporates and condenses again, forever, in a cycle of storm, without end and without purpose. Imagine standing impossibly on a platform in those clouds. The sky above you is a furnace. The wind arrives before sound itself could warn you, and glowing threads of liquid glass streak past you in the dark like tracer fire. And the star is not finished with this planet. HD 11897333b orbits so close to its sun that it lives inside the weather of the star itself, and its star is an active one, prone to flares. Astronomers watching the system with the Hubble Space Telescope have caught something remarkable. Observations suggesting that after a powerful X-ray flare from the star, the planet's upper atmosphere was seen escaping, hydrogen streaming away into space at enormous speeds. The star doesn't just heat this world, it erodes it, stripping its outer layers particle by particle. The blue planet is being slowly sandblasted by its own sun, and it has no way to leave. Over billions of years, a hot Jupiter like this may lose a meaningful fraction of itself this way, shedding its substance into space like smoke off a candle it can never escape. Here is the thought that lingers though. From 64 light-years away, none of that violence is visible. From here, HD 11897333b is simply a lovely blue dot beside an orange star. Astronomers sometimes point out that if some other civilization somewhere out there measured the color of our planet the way we measured the color of this one, they would see almost the same thing. A small, deep, blue world. The same postcard. They would have no way of knowing at first whether they had found an ocean or a storm of glass. Color, from a distance, keeps its secrets. It's a humbling reminder that beauty and hostility are not opposites out there. In the universe's catalogue of worlds, they are very often the same entry. So HD 189733b teaches us the first rule of this tour: appearances mean nothing. Now, let me show you what happened when astronomers found a planet with no appearance at all. A planet that is barely there when you look for it. A planet made of darkness. About 700 light years away, in the constellation Draco the Dragon, a star not so different from our Sun carries a planet called rarest 2b. It was discovered in 2006 by a modest network of small telescopes, and for a few years it seemed unremarkable. A typical hot Jupiter, roughly the mass of Jupiter, roughly the size of Jupiter, orbiting its star at a distance of only about 5 million kilometers, completing a year in about 2.5 days. By then, astronomers had found dozens like it, but rarest 2b happened to sit in the patch of sky watched by the Kepler Space Telescope, the most sensitive light-measuring instrument ever pointed at the stars. And when scientists used Kepler to study this ordinary planet, they found something that made headlines around the world. They found a world that refuses to shine. Every planet we had ever known reflects light. It's the only reason we see them at all. Venus blazes in our evening sky because its clouds bounce back around 3/4 of the sunlight that touches them. Earth reflects roughly 1/3 of its light, all that white cloud and blue water flashing into space. Even our moon, which is actually quite dark, made of grey volcanic rock, still reflects enough light to flood our nights with silver. Astronomers call this reflectiveness albedo, and before Kepler, every planetary albedo we had ever measured told the same basic story. Worlds shine. Then came the measurement of rarest 2b. This planet reflects less than 1% of the light that falls on it. Less than 1%. It is darker than coal, darker than black acrylic paint, darker than the blackest volcanic rock on Earth. It is, by measurement, less reflective than almost any surface humans have ever manufactured, and it is the darkest planet ever discovered. Try to picture it and notice that you almost can't. That's the point. Coal held in sunlight still shows you its edges, its texture, its glints. rarest 2b would show you almost nothing. A Jupiter-sized planet, 140,000 kilometers across, hanging directly beside its blazing star, receiving a flood of light every second, and giving essentially none of it back. If you could somehow float nearby and look at the place where the planet should be, you would see a hole. A round absence, a coin of pure black punched out of a sky full of stars betrayed only by the starlight it blocks. Astronomers who worked on the discovery reached for comparisons and came up with the same unsettling phrase again and again. It is blacker than coal. A world of black moving silently around its sun. It's worth pausing on how a measurement like that is even possible, because nobody photographed this darkness. Kepler watched the rarest 2 system for months, recording its combined brightness, star and planet together. As the planet circled, it showed phases, exactly like our moon, a lit crescent growing toward a lit face and shrinking back. If the planet reflected light like a normal world, the system should brighten, just barely, whenever the planet's day side turned toward us. Astronomers combed the data for that rhythmic brightening and found it almost absent. The flicker they finally teased out was on the order of a few parts per million, among the most delicate light variations ever measured in astronomy at the time. Think about the confidence of that claim. From 700 light-years away, using no image at all, only arithmetic on starlight, we can say with certainty that a particular world is darker than any coal seam on Earth. When people say astronomy is the art of extracting the maximum meaning from the minimum light, this is what they mean. Why? Why would a planet swallow light? The honest answer, and this is what makes rarest 2b more than just a curiosity, is that we still don't completely know. Part of the explanation is temperature. This planet orbits so close to its star that its atmosphere is heated beyond 1,000 degrees Celsius. On a cooler giant planet like Jupiter, sunlight is bounced back by high, bright clouds of ammonia ice. Rarest 2b is far too hot for ammonia clouds, or for water clouds, or for almost any of the bright condensates that make planets shine. Its skies are clear in the worst possible way. Clear of everything except light-absorbing vapors. Its atmosphere is laced with chemicals like gaseous sodium and potassium and titanium oxide, substances that don't scatter visible light, but drink it. Sunlight enters that atmosphere, and layer by layer, atom by atom, it is simply absorbed, its energy dissolved into heat. But here's the uncomfortable footnote that scientists themselves added. When they built models of that atmosphere, with all the light-absorbing chemistry they could reasonably include, the models still could not fully explain how dark this planet actually is. The known ingredients account for much of the darkness, not all of it. Something in the skies of rarest 2b is eating light in a way we have not yet identified. It is probably ordinary chemistry we haven't pinned down, some molecule or haze we haven't thought to include. But, as of now, the darkest world we know keeps a fraction of its darkness unexplained. And rarest 2b is not perfectly black. This is my favorite detail, the one that turns the planet from a void into a place. It is so hot that it glows, not with reflected light, but with its own heat, the way an electric stove element glows after you switch it off. If you could approach that black world safely, you would see, along its darkest reaches, a faint, deep red smolder, like the last embers of a dying fire, like coals breathing in the dark. A planet that gives back none of its star's light, shining anyway dimly in furious red, with heat it cannot contain. Somewhere out there, 700 light-years from your pillow, that ember is circling its star right now, once every 2.5 days, wrapped in a darkness we can measure but not yet fully explain. 2 planets in, and look at how thoroughly the universe has already dismantled our expectations. A blue world where the blue means glass and fury instead of water and calm. A black world that swallows light for reasons we can't completely name. But both of those are gas giants, worlds with no surface, no ground, no geography. The next planet on our journey is different. It is a rocky world like ours. A super-Earth, the astronomers call it. It has a surface you could, in principle, stand on. And that is precisely what makes it so much worse. 41 light-years away, in the constellation of Cancer, there is a star you can actually see. On a clear, dark night, away from city lights, the star 55 Cancri is faintly visible to the naked eye. Think about what that means. Of all the worlds we will visit tonight, this is the one whose sun you could stand outside and find, a real point of light your own eyes can catch. People have been unknowingly glancing at that star for as long as people have looked up, and circling it so close to its surface that its entire year lasts less than a single Earth day is one of the most hellish, rocky worlds ever discovered. Its name is 55 Cancri E. Let's start with the numbers, because the numbers are the story. 55 Cancri E is what astronomers call a super-Earth, a class of planet our solar system doesn't contain, larger than Earth but smaller than Neptune. It is about twice the diameter of Earth and roughly 8 times the mass. Gravity at its surface would pin you down at nearly twice your current weight. But it is the orbit that defines this world. 55 Cancri E circles its star at about 1/25th of the distance between Mercury and the Sun. Its year, one complete trip around its Sun, lasts about 18 hours. 18 hours. You have lived through longer days than this planet's entire year. If you fell asleep on 55 Cancri E at midnight and slept your usual 8 hours, you would wake up nearly half a year later. This planet isn't alone either. The star 55 Cancri hosts a whole family, 5 known planets, making it one of the richer planetary systems in our neighborhood, and 55 Cancri E is the smallest and innermost of them, the child sent closest to the fire. It even has a proper name. In 2015, when the International Astronomical Union invited the public to name a first group of exoplanets, this world was given the name Janssen, after the spectacle maker often credited with helping invent the earliest telescopes, and its star was named Copernicus. There is something quietly fitting in that pairing. The man whose lenses first extended human sight, remembered forever in the name of a world that no lens will ever show us directly. Being that close to a star does something irreversible to a rocky world. The planet is almost certainly tidally locked, one face aimed at the star forever. And on that day's side, the temperature does not merely rise, it passes the melting point of rock and keeps going. Measurements put the day side at well over 2,000 degrees Celsius, and some observations have suggested it may at times run far hotter. At those temperatures, the concepts we use to describe a landscape stop working. There is no ground, in any sense, you would recognize. The surface of the day side is almost certainly an ocean of lava, not a lava field, not volcanoes scattered across a plain, an ocean. A planet-wide rolling sea of molten rock, glowing yellow-orange from horizon to horizon, with no shore on the day side to interrupt it, its slow current stirred by the raw heat of a star that fills a huge portion of the sky and never, ever sets. And above that ocean, the sky itself is made of rock. On a world where stone evaporates, the atmosphere fills with vaporized minerals. Astronomers studying this planet have proposed skies containing silicate vapor, the boiled essence of rock rising off the lava ocean, the way steam rises off hot water. On the cooler night side, that mineral steam could condense and fall, rock raining onto rock. There is even a formal scientific observing program with time on major telescopes that asked, in essentially these words, whether it rains lava on 55 Cancri E in the evening. That is not a phrase from a fantasy novel, that is a research question about a real place, 41 light years from your bed. And what of the other half of Janssen, the night side, the hemisphere that has never once seen its star? Cross the Terminator in your imagination and descend into that permanent dark. It is still ferociously hot by Earth standards, heat carried around from the day side by the newly discovered atmosphere and conducted through the body of the planet itself. But compared to the lava hemisphere, it is almost restrained. Here, the mineral vapor lifted off the day-side ocean may cool enough to condense. If it does, then somewhere on the night side of that world, the sky sheds droplets of liquid rock, or perhaps even flakes of solidifying mineral, rock falling as something like snow, drifting down through the dark onto a surface that may hold the only solid ground on the planet. A hemisphere of black glass fields, perhaps, built flake by flake out of the boiled away substance of the other side. No one has seen it. No one can, yet. But the physics points somewhere extraordinary, a world with one hemisphere of glowing ocean and one hemisphere of dark stone welded back to back, forever facing opposite ways. For a while, this planet carried an even stranger nickname. Early estimates of its composition suggested it might be extraordinarily rich in carbon, and under the pressures inside a planet like that, carbon takes a form you know very well: diamond. For a few years, headlines called 55 Cancri the Diamond Planet, a world whose interior might hold a layer of crystalline diamond bigger than the Earth itself. Later, measurements walked this back. The star turned out to be less carbon-rich than first thought, and with it, the planet's diamond credentials faded from likely to merely possible. Science does this, and it's worth loving science for it. The universe is allowed to be less dramatic than our headlines, but hold on to that image for a moment anyway, because even the sober version of this world, the version without the diamonds, is a planet of glowing seas under a sky of mineral steam. Then, very recently, the story took another turn, and this one made 55 Cancri E more interesting, rather than less. For years, astronomers argued about whether a planet this scorched could hold any atmosphere at all. A star that close doesn't just heat a planet, it sandblasts it with radiation and wind, stripping gas away into space. Most scientists expected bare rock, or at most a thin mist of vaporized stone. Then the James Webb Space Telescope turned its instruments on the planet, watching its infrared glow as it slipped behind its star. And the readings pointed somewhere unexpected, The day side was cooler than it should be if bare rock was simply soaking up starlight. Something was moving heat around the planet, carrying energy from the day side toward the night side. The most compelling explanation is a real atmosphere, likely rich in carbon dioxide or carbon monoxide, possibly bubbling continuously out of the magma ocean itself. An atmosphere exhaled by a sea of lava. On the most tortured, rocky world we know, the planet appears to be breathing. There is one more detail, and it is the one I find hardest to forget. Because we have watched this planet for years, we've noticed that it changes. Its heat signature has varied dramatically from one observation to the next, as if the entire planet sometimes dims and sometimes flares. Recent work suggests a remarkable mechanism, a feedback loop between the magma ocean and the sky. The lava heats up and boils mineral vapor into a reflective haze. The haze shades the ocean, which cools and stops producing vapor. The sky clears, the stars' full fury returns, the ocean heats up again, and the cycle repeats. If that's right, then 55 Cancri E has weather in the fullest sense. Seasons of steam and clarity, driven not by rain and sunshine, but by the boiling and settling of rock itself. A planet locked in a permanent argument with its own sky. Now, you might reasonably think a world of lava oceans is as extreme as planetary weather can get. The universe disagrees, because everything we've seen so far, glass rain, light-swallowing skies, molten seas, still involves familiar substances behaving badly. The next world on our journey does something different. It takes one of the strongest, most solid materials in your everyday life, the metal in your cutlery, your car, the frame of the building around you, and it turns that metal into weather. 640 light-years away in the constellation Pisces orbits a giant planet called WASP 76b. The name comes from the survey that found it in 2013, the Wide-Angle Search for Planets, a program that watched huge swathes of sky for the telltale dimming of stars. WASP 76b is another hot Jupiter, comparable in mass to Jupiter itself, but puffed up by heat to nearly twice Jupiter's size, and it circles its star in just 1.8 days. By now, you know what that proximity means. Tidal locking, one face in eternal daylight, one face in eternal night. But WASP 76b became famous because astronomers managed to do something remarkable with it. Using an instrument called Espresso on the European Southern Observatory's Very Large Telescope in Chile, they didn't just detect the planet's atmosphere. They watched its weather happen, tracking chemistry across the boundary between day and night. Here is what they found. The day side of WASP 76b reaches temperatures above 2,400 degrees Celsius. That is not just hot enough to melt iron, it is hot enough to boil it into vapor. On the day side of this planet, iron does not exist as metal, it exists as a gas, an invisible component of the sky, iron atoms drifting free in the furnace air, the way water vapor drifts through a summer afternoon on Earth. Sit with that image. The hardest, most dependable metal of human civilization, the stuff we build skyscrapers and bridges from, reduced to a vapor in the atmosphere, because the sky itself is hotter than a blast furnace. But a tidally locked planet always has two faces, and the night side of WASP 76b, while still a hellish 1500 degrees or so, is crucially cooler than the day side. Cooler enough that iron vapor cannot survive there as vapor. So consider what must happen. Ferocious winds, driven by that enormous temperature difference, sweep the day side's air toward the night side, carrying the vaporized iron with them. The air crosses the terminator, the eternal boundary line between day and night, into the darkness. It cools, and the iron condenses, first into clouds of iron, and then, as the droplets grow too heavy for the sky to hold, into rain. Molten iron rain, glowing liquid metal, falling through the permanent night of a world 640 light-years away. The astonishing part is that this isn't inference alone. The astronomers could see the signature of iron vapor on the evening edge of the planet, where day-side air flows into night, and then found it missing on the morning edge where night-side air rotates back into day. The iron enters the night side and does not come out. Somewhere in that darkness, it falls. The lead scientists put it simply: it rains iron on the night side of WASP 76b. Evening on that world, if you could hover in its high clouds, might look like this. Behind you, over the horizon, a furnace glare where the star never sets. Around you, a scalding wind moving at thousands of kilometers per hour. And ahead, in the endless dark, sheets of red-hot metal rain, glowing as they fall, lighting the clouds from within like slow lightning. Stand for a moment at the terminator of WASP 76b, the eternal boundary between its day and its night, because it may be one of the most dramatic locations in the known galaxy. This is the line the iron crosses. Behind you, a hemisphere of permanent furnace glare, a sky of vaporized metal, a star 40 times larger in the sky than our sun appears from Earth, fixed in place, never moving, never setting. Ahead of you, a hemisphere of endless darkness, glowing faintly at its edges with its own residual heat. And directly above you, at the crossing line, the winds howl past, carrying their invisible cargo of iron vapor into the dark, where somewhere beyond the horizon it cools, gathers, and falls. Every evening line on every world has some version of this handover, day passing its heat to night. On Earth, the handover is so gentle we've made it the most romantic hour of the day. On WASP 76b, the same hour, the same line, the same physics, delivers rains of molten metal. There's a strange comfort hiding inside this planet's story, and it's worth pausing on. Nothing happening on WASP 76b is exotic physics. It is the water cycle, evaporation, wind, condensation, rain. The exact process that waters your garden, lifted whole and applied to a different substance at a different temperature. The universe, it turns out, doesn't invent new machinery for its most extreme worlds. It runs the same familiar machinery under conditions we can barely imagine. Rain is rain, whether it is water on Earth, glass on HD 199733b, or iron in the night of WASP 76b. When you hear rain against your window, you are listening to the same physics that lights the night clouds of a world where metal falls from the sky. The universe has only a few songs. It just plays them at very different volumes. And yet even WASP 76b, a planet that vaporizes iron, is not the hottest world we have found. Not even close, really. The next planet on our journey is so extreme that calling it a planet at all starts to feel like a technicality. It is a world caught in the space between planet and star, hotter than some stars actually are. A place where the very molecules of its atmosphere cannot hold themselves together, and it is dying in a way we can watch. About 670 light-years away in the constellation Cygnus, the Swan, there is a star called Kelt 9. It is not a gentle star like our Sun. It is nearly twice as hot as the Sun, a blue-white furnace spinning so quickly that it bulges at its equator, pouring out radiation with a violence our own star will never approach in its entire life. And in 2017, astronomers announced that this star has a planet. A gas giant nearly 3 times the mass of Jupiter, orbiting so close that its year lasts about a day and a half. They named it Kelt 9b, and from the moment of its discovery, it has held a title that no other confirmed planet has managed to take. It is the hottest planet ever found. There's a lovely irony in how this extreme world was found. Kelt stands for kilodegree, extremely little telescope, and the name is a joke with a straight face. In an era of giant observatories with mirrors the size of swimming pools, the Kelt survey used equipment closer to a professional camera lens, tiny, humble instruments watching huge swaths of bright stars that the big telescopes ignored. The most extreme planet ever discovered was not found by humanity's mightiest eye. It was found by one of its smallest, pointed patiently at the right patch of sky. Astronomy keeps teaching this lesson. The universe doesn't only reward power, it rewards attention. Here is the number. The day side of Kelty 9b reaches temperatures around 4,300 degrees Celsius. I want to make sure that number lands properly, because our minds are not built for it. 4,300 degrees is not simply hotter than any place on Earth. It is hotter than lava by a factor of nearly 4. It is hot enough to vaporize, not melt, vaporize, essentially every material humans have ever worked with: iron, titanium, tungsten, diamond. At the temperature of Kelton 9b's day side, all of them are gas. But the comparison that matters is this one. That temperature is hotter than the surface of some stars. There are entire stars in our galaxy, small, dim, red dwarf stars, quietly fusing hydrogen in their cores as true stars do, whose surfaces are cooler than the day side of this planet. When astronomers measured it, the day side of Kelty 9b came out only about 1,000 degrees cooler than the surface of our own sun. This is a planet that has crossed a line we didn't know a planet could cross. It is a world with the temperature of a star. At that temperature, the ordinary idea of an atmosphere begins to disintegrate. Literally, air, any air, is made of molecules, atoms holding hands in stable pairs and groups. Water is an oxygen atom holding two hydrogens. The nitrogen in every breath you take is two atoms bound together. Molecules can survive heat, but only so much of it. Somewhere above 3,000 degrees, the shaking becomes too violent and the bonds start to break. On the day side of Kelt 9b, it is so hot that even molecular hydrogen, the simplest and most stubborn molecule in the universe, 2 protons and 2 electrons in the tightest of embraces, is torn apart. The day-side sky of this planet is not made of molecules. It is a fog of broken atoms, single hydrogens drifting alone alongside vaporized iron and titanium that astronomers have directly detected in its outer atmosphere. Metal as sky. But those atoms do not stay on the day side. Enormous winds carry them around the planet, across the terminator, into the night. And on the night side, merely blisteringly hot instead of star hot, something quietly beautiful happens. The broken hydrogen atoms find each other again. They recombine into molecules, releasing a whisper of energy as they bond, and for a while the night sky of Kelty 9b is made of whole hydrogen again. Then the planet's orbit and the roaring winds drag that air back around into the day, and the star tears every molecule apart once more. Break and mend. Break and mend. A planet-sized cycle of destruction and reunion, repeating every day and a half, forever. Somewhere in the galaxy right now, on a world we will never visit, hydrogen is being shredded at noon and healing itself at midnight. The strangeness of this system runs even deeper than temperature, because Kelty 9b doesn't orbit its star the way planets are supposed to. It orbits over the poles. Instead of circling its star's equator, the way every planet in our solar system roughly circles the sun's, Kelt 9b travels a nearly polar path, passing over the top of its star, then around the bottom on every 36-hour circuit. And its star is spinning so fast that it isn't truly round. The rotation flings the star's equator outward, and that bulging equator runs measurably cooler than the poles by something like 800 degrees, which produces one of the most wonderful facts in the entire exoplanet catalogue. As Kelty 9b swings over each searing pole, it receives extra heat, and as it crosses the cooler equatorial region, it receives less. Summer at the poles, winter at the equator. The planet experiences 2 summers and 2 winters every orbit, a complete 4-season year compressed into a day and a half, with each season lasting about 9 hours. Somewhere out there is a world where an entire year of seasons passes in the time between your dinner and your breakfast, and Kelt 9b is paying for its position with its life. A planet that hot cannot hold on to itself. The star's radiation pumps so much energy into the atmosphere that the outermost layers simply boil away into space. Astronomers observing the system with the Hubble Space Telescope have detected heavy metal ions, magnesium and iron, escaping the planet entirely, streaming beyond the gravitational boundary where the planet could ever pull them back. Kelt 9b is evaporating. It is likely trailing its own dissolving atmosphere behind it like a comet's tail, a giant planet unraveling thread by thread into the dark. It will take a very long time by human standards, and the planet is massive enough that it may hold out for the life of its star. But the direction of the story is set. The hottest planet we know is a planet being slowly erased. If you want to see the ending of that kind of story, you only have to look at a different star in a different part of the sky. Roughly 1,400 light-years away, a planet called WASP 12b is in the final act. It is a hot Jupiter, discovered in 2008, circling its yellow star in just over a single Earth day, so close that the star's gravity has physically pulled the planet out of shape. WASP 12b is not a sphere. Tidal forces have stretched it into something closer to an egg, its substance leaning perpetually toward the star that grips it, and measurements suggest its skies may hover above 2,000 degrees, its outer layers swollen and loosely held. But that is not why this planet matters tonight. It matters because of what careful clock watching revealed. Astronomers timed its transits year after year, the way you might time a runner's laps, and the laps are getting shorter, not by much, by about 30 milliseconds per year. But the meaning of those milliseconds is enormous. The orbit is shrinking. WASP 12b is the first planet in history where we have directly confirmed the long-predicted fate of worlds that dare to orbit too close. It is spiraling into its star. The energy of its orbit is draining away, converted into tides and heat, and every single year brings it measurably closer to the surface of its sun. The projected timeline gives it roughly 3 million years. Then the star will simply take it. 3 million years sounds like an eternity, and by our lives, it is. But the dinosaurs vanished 66 million years ago. On the calendar of the universe, WASP 12b's remaining time is a rounding error. We are watching in real time the last few pages of a planet's existence. It's worth dwelling on what the ending will actually look like, because nothing in human experience prepares us for the death of a planet. As the orbit tightens over those final ages, the star's tidal grip will strengthen, and the egg shape of WASP 12b will grow more pronounced, the planet's substance drawn further and further toward its sun. At some point, the pull will win outright. The planet's outer layers will begin streaming onto the star in earnest, a bridge of glowing gas connecting world to sun, the planet unraveling like a ball of thread caught on a spinning wheel. And eventually, what remains will cross the invisible line where the star's gravity overwhelms the planet's own, and WASP 12b will come apart, its billions of years of existence dispersed into a hot ring of debris, swallowed, absorbed, incorporated. The star will barely register the meal. A brief flicker of extra brightness, perhaps a subtle change in its chemistry, the ghost of a planet dissolved into a stellar atmosphere. Then nothing. Every atom of that enormous world still existing, but no world anymore. Somewhere in deep time, our own sun, swelling into a red giant near the end of its life, may do something similar to Mercury, to Venus, perhaps to Earth itself. When we watch WASP 12b, we may be previewing, at a safe distance of 1,400 light-years and 5 billion years, the last chapter of our own address. Let that settle for a moment and notice what these worlds have in common. Every planet we visited so far suffers for the same single reason: closeness. Each of them orbits tight against its star, and the star's heat and gravity dictate everything: the glass rain, the iron rain, the lava seas, the shredded molecules, the death spiral. You might reasonably conclude that distance is safety, that a planet farther out on a wider orbit escapes the horror. And that is exactly why our next world is so unsettling, because the next planet on our journey spends most of its time at a perfectly respectable, perfectly safe distance from its star. Its problem is that it doesn't stay there. The planet is called HD 80606b, and it lies about 200 light-years away, toward the constellation Ursa Major, the Great Bear. It is a gas giant about 4 times the mass of Jupiter, and when it was studied closely, astronomers found the most extreme orbit of any transiting planet known. To understand it, picture the orbits you were taught. Earth's path around the Sun is so close to a perfect circle that a drawing of it looks like one. Even the other planets of our solar system follow gently oval paths. Astronomers measure this ovalness as eccentricity, on a scale where 0 is a perfect circle and 1 is an orbit so stretched it never closes at all. Earth's eccentricity is under 0.02. Pluto, famously elongated, is about 0.25. The eccentricity of HD 80606b is 0.93. That is not the orbit of a planet. That is the orbit of a comet. Something in this system's past, perhaps the slow gravitational influence of the companion star that shares its sky, wrenched this giant planet out of whatever circle it was born on and left it on a path of extremes. Follow it through one circuit. For most of its 111-day year, HD 80606b swings far from its star, out to a distance comparable to Earth's distance from the Sun, over 120 million kilometers. Out there, it cools and drifts through a long, quiet season. Then it begins to fall. Week by week, it accelerates inward, the star swelling in its sky until it whips around its sun at a distance of less than 5 million kilometers, 13 times closer than Mercury ever comes to the sun. Then it is flung back out into the cold to begin again. In the 30 hours surrounding that closest approach, the energy pouring onto the planet increases by a factor of about 830. 830 times more starlight in barely more than a day. There is no equivalent anywhere in our solar system. It is as if a world spent months in an Arctic dusk and was then, without transition, thrust into the flame of a furnace and pulled back out before it could even finish igniting. How does a planet end up on a path like that? The system offers a suspect. The star HD 80606 is not alone. It has a twin, a companion star called HD 80607, close enough that the two are gravitationally bound. A double-star system where the two suns circle each other across the ages. The leading idea is that over millions of years, the companion star's distant, patient gravitational influence could have slowly tilted and stretched the planet's original orbit, pumping it into today's extreme ellipse, a process astronomers can model mathematically and observe in various stages elsewhere. If that's right, then HD 80606b is a planet whose fate was written by a star it never even orbited. And the discovery of its true nature took years of detective work. The planet was first found in 2001 through the wobble of its star, and the wild eccentricity was clear from the start. But it took until 2009 for astronomers to catch it transiting, crossing the face of its star as seen from Earth, a crossing so slow, thanks to that stretched orbit, that the transit lasts nearly 12 hours from start to finish. We know what that moment does to the planet because we watched it happen. In one of the Spitzer Space Telescope's most celebrated observations, astronomers monitored HD 80606b continuously for 85 hours as it made its closest approach. They watched the temperature of its atmosphere climb from around 500 degrees Celsius to over 1100 in a matter of hours. The planet's sky more than doubled its temperature in less than a day. Computer models of that event suggest the heat detonates global storms, winds erupting to enormous speeds, shockwaves of heated air racing around the planet as its atmosphere struggles to absorb a year's worth of fire in a single afternoon. And then, just as remarkably, they watched it cool. Within about 10 hours of rounding the star, the planet's glow faded dramatically, its skies shedding heat back into space, the storm slowly wringing itself quiet as the world climbed back out into the dark. Here is the image I can't shake. Every world we visited tonight lives in a kind of terrible equilibrium. The glass rain of HD 19733b never stops. The lava ocean of 55 Cancri E never cools. Their extremes are constant, and there is almost a mercy in that constancy. HD 80606b is different. It is a world defined by anticipation. For 100 days, almost nothing. Cold, calm, a distant bright star among stars, and always, on a schedule as reliable as any calendar, the fall comes, and the fire, and the long climb back out. If that planet has any permanence at all, it is the permanence of the cycle itself. Approach, burn, retreat, recover. It has repeated that loop in silence for billions of years with no one to witness it until a small, warm telescope from Earth happened to be watching in January of 2009. By now you may have noticed the shape of tonight's journey: fire, darkness, molten rock, falling metal, worlds being unmade. Every stop so far has been a variation on violence. So before we descend into the strangest systems of all, I want to pause somewhere different. Because not everything the universe builds in defiance of our expectations is hostile. Some of it is simply quietly wrong in the most wonderful way. The next world on our journey wouldn't hurt you at all, at least not quickly. It is cold, calm, and stately. What makes it impossible is not its weather, it's the number of suns in its sky. For as long as we have told stories about other worlds, we have imagined double sunsets. Two suns hanging over an alien horizon is perhaps the single most iconic image in all of science fiction, the universal shorthand for standing somewhere that is not Earth. And for decades, planetary scientists quietly doubted it could exist. The concern was simple gravity. A planet orbiting two stars at once is a planet with two masters. Each star pulls on it constantly. From constantly changing directions and calculations suggested that in many two-star systems, a planet's orbit would be stretched and worked and destabilized until the planet was either hurled out of the system entirely or torn from its path and destroyed. Around a close pair of stars, the thinking went, planets simply shouldn't be able to form or survive. The double sunset was a beautiful idea that physics seemed inclined to veto. Then, in September of 2011, the Kepler Space Telescope found Kepler-16b. About 200 light-years away, in the constellation Cygnus, two stars orbit each other closely, circling their common center every 41 days. One is a modest orange star, about 2/3 the mass of our Sun. The other is a small red dwarf, only about 1/5 of a solar mass. And around both of them, around the pair as a whole, moves a planet. Kepler-16b is roughly the mass of Saturn, a cold world of rock and gas, and it circles its two suns together, both of them at once, completing its wide loop every 229 days. There was no ambiguity in the discovery. The planet passes in front of both stars, dimming each in turn, its crossings woven into the rhythm of the stars, eclipsing one another. The data showed 3 bodies, 2 stellar and 1 planetary, locked in a gravitational dance that scientists could reconstruct with beautiful precision. The first confirmed planet with 2 suns. The astronomers who announced it couldn't resist the comparison, and neither will I. Tatooine is real. It's just 200 light-years farther away than a movie screen. Stand there for a moment in your imagination. Kepler-16b itself is probably no place for standing. Like Saturn, it is likely mostly gas wrapped around a dense core, and it is cold, orbiting at the outer edge of its system's warmth, with cloud-top temperatures far below freezing. But give it, in your mind, a rocky moon to stand on, which is entirely possible, and look up. 2 suns cross the sky together, one larger and orange, one smaller and red, and they are not fixed in place relative to each other. They orbit each other every 41 days, so some days they hang apart, twin lights in a pale sky, and some days they draw together, and on special days one slides directly in front of the other. Sunset is doubled. The orange sun goes down and the light changes, and then the red sun follows, and the land or the clouds pass through a second dusk of deep crimson before true night arrives. No fire, no molten rain, just a sky with one more sun than any sky you will ever see, repeating its slow choreography over a frozen world that wasn't supposed to exist. And if you stood there long enough, you would learn to tell time by shadows. 2 suns means 2 shadows. Everything on that imagined moon would cast a pair of them, one orange-edged and one red, stretching in slightly different directions, lengthening and crossing and merging as the twin suns wheeled overhead on their 41-day dance. Every rock a sundial with 2 hands. When the stars eclipse each other, one shadow dissolves, and for a few hours the world is lit by a single sun, like ours, before the second light returns. It's such a small detail, shadows, but nothing communicates how deeply another world differs from ours, like realizing that even the shadows work differently there. Kepler 16b matters for a reason bigger than its beauty. It was a proof. Within just a few years of its discovery, astronomers found more circumbinary planets, more worlds with 2 suns, enough to make clear that Kepler 16b was not a freak survivor, but a member of a real planetary family. Planets, it turns out, can form and persist in gravitational environments we once wrote off as impossible. Hold on to that lesson, because it is about to be tested far more brutally. 2 suns was supposed to be too hostile for planets, and the universe shrugged and made them anyway. So what about no functioning sun at all? What about a star that has already died as violently as physics allows? Surely there, at least, planets are impossible. To answer that, we travel now to the system I promised you at the start of the night, 2,300 light-years away, in the constellation Virgo, to the first exoplanets humanity ever confirmed, and to the strangest sun in this entire story. The object at the center of that system is called PSR B257+12, and it is a pulsar. To understand what that means, you have to watch a giant star die. A star many times the mass of our sun spends millions of years burning through its fuel, fusing lighter elements into heavier ones, holding itself up against its own crushing gravity with the outward pressure of that burning. Then, one day, the fuel runs out. The pressure fails, and the core of the star collapses all at once, in a fraction of a second, while the outer layers detonate in a supernova, an explosion that can briefly outshine an entire galaxy of hundreds of billions of stars. What remains at the center is one of the most extreme objects in the universe, a neutron star, the mass of a sun or more, compressed into a sphere perhaps 20 kilometers across, the size of a city. Matter packed so densely that a single teaspoon of it would outweigh a mountain range. Some neutron stars, as they collapse, are spun up like ice skaters pulling in their arms, and they emit beams of radiation from their magnetic poles. As the star spins, those beams sweep across space like the beams of a lighthouse. If Earth happens to lie in the path of the sweep, our radio telescopes detect a pulse, a metronomic flicker, arriving with a regularity that rivals atomic clocks. We call these objects pulsars. And PSR B257+12 is an extraordinary one, even by pulsar standards. It is a millisecond pulsar. It rotates this entire city-sized mass of collapsed star more than 150 times every second, nearly 10,000 rotations per minute. An object heavier than the sun, spinning like the blade of a kitchen blender, 2,300 light-years from your bedroom. The instrument that found this system deserves its own remembrance. The Arecibo Observatory, built into a natural sinkhole in the hills of Puerto Rico, was for more than half a century the largest single-dish radio telescope on Earth, a bowl of perforated aluminum 305 meters across, big enough to hold several sports stadiums, with its receivers suspended on cables hundreds of feet above the dish, like a spider over a silver web. Generations of astronomers listened to the universe through it. It survived hurricanes and earthquakes and decades of weather until its support cables finally failed. And in December of 2020, the instrument platform came down and the great dish was destroyed. The telescope that found the first planets beyond our solar system no longer exists. The planets it found are still there. There's something worth holding on to in that asymmetry. Our instruments are mortal. What they discover is not. In 1990, the Polish astronomer Alexander Wolszczan was observing with that enormous Arecibo dish when he found this pulsar's signal. Its pulses arrived thousands of times per second, and they should have been perfectly, monotonously regular. They were not. The pulses came very slightly early, then very slightly late, in slow repeating patterns, as if the pulsar itself were being gently rocked back and forth. Wolszczan and his colleague Dale Frail analyzed those tiny timing shifts and came to a conclusion that stunned the astronomical world. The dead star was wobbling because things were orbiting it. Planets. 2 of them at least, each roughly 4 times the mass of Earth, one circling every 66 days, the other every 98. In 1992, they published the result, and it became the first confirmed discovery of planets outside our solar system in human history. 2 years later, continued timing revealed a third, far smaller world, closer in with only about twice the mass of our moon, one of the smallest objects ever detected around another star. Before we found a single planet around a single living, sun-like star, we found a whole family of them orbiting a corpse. Appreciate, for a moment, the sheer precision of that discovery, because it may be the most delicate measurement in this entire night's journey. A millisecond pulsar is one of the best natural clocks in the universe, its pulses arriving with a regularity that pushes against the precision of atomic clocks on Earth. That is the only reason this discovery was possible. The planets do not dim the pulsar or light it up or cast any shadow we can see. All they do is pull it gently by a few hundred kilometers this way and that as they orbit. That tiny displacement changes the distance the radio pulses travel to reach us, which shifts their arrival times by fractions of a millisecond. From those fractions, Wolszczan and Frail reconstructed an entire planetary system, the masses of the worlds, the shapes and periods of their orbits, sight unseen, across 2,300 light-years. It remains one of the most astonishing acts of measurement in scientific history. We found the first planets beyond our solar system not by seeing them, but by noticing that a dead star's clock was running almost imperceptibly strangely. Sit with how strange that is. These planets should not exist. The supernova that created the pulsar would have devastated any planetary system the original giant star possessed, scouring and scattering whatever worlds it once held. The most likely explanation is stranger than survival. Astronomers believe these planets are second-generation worlds. After the catastrophe, some of the wreckage, debris from the explosion or the remains of a shredded companion star, settled into a disk around the newborn pulsar, the same kind of disk of dust and rubble that once circled our young sun. And out of that graveyard disk, gravity did what gravity always does. It gathered the fragments, it built new worlds out of the ruins of the old, and set them in clean, stable orbits around the very object whose birth had destroyed everything before. The universe does not merely permit planets in unlikely places, the universe rebuilds them on top of its own wreckage. When the International Astronomical Union eventually invited the public to help name these worlds, the names chosen were fittingly Gothic. The tiny innermost planet is Drauga, named for the undead of Norse legend. The others are Poltergeist and Phobitor, a ghost and a bringer of nightmares. Planets of the dead, named for the dead. And their sky earns the theme. If you could stand on Poltergeist, you would not see a sun, in any sense you know. The pulsar would be far too small to show a disk, a searing point of light, dimmer invisible light than our sun, yet lethal in what you cannot see, because it pours out radiation across the spectrum, gamma rays and X-rays and charged particles, sterilizing the system it built. Some scientists speculate that the pulsar's wind of particles washing over those planets' skies might light them with permanent aurorae, entire atmospheres. If atmospheres exist there, glowing like the polar skies of Earth. 3 dark worlds, wrapped in curtains of ghost light, circling a spinning point of poison in the silence for billions of years, with nobody to know they were there, until a radio telescope on a warm green island happened to be listening. The pulsar planets complete a progression you may have already noticed. We started tonight with worlds ruined by too much sun, then a world with 2 suns, then worlds whose sun is a corpse. There is exactly 1 step left, and the universe has taken it. The last worlds on our journey tonight have no sun at all. Not a dying one, not a dead one, none. They are the loneliest objects ever conceived, and there may be more of them than there are stars in the sky. Every world you have ever imagined has a sky with something in it, a sun or 2 suns, or at least the searing spark of a pulsar. Every planet we visited tonight, however tortured, belongs to something. It has a center to its year, a light to define its day, a gravitational anchor to call home. Now I want you to imagine a planet with none of that. A planet that orbits nothing. It does not circle a star. It does not belong to a system. It moves through the galaxy alone on its own long path around the galactic center, through the empty spaces between the stars. On this world, the sun never rises because there is no sun. There is no day, and there never will be. There is only a single permanent, eternal night under a sky of stars that never grow closer. Astronomers call these objects rogue planets or free-floating planets, and they are not rare. They may outnumber every star you have ever seen. The first question is obvious. How does a planet end up with no star? The answer takes us back to how planets are born, and it turns out that planetary birth is far more violent than the serene textbook illustrations suggest. Planets form in crowds, condensing out of the disk of gas and dust around a young star, and young planets do not stay politely in their lanes. They migrate. They drift inward and outward, their orbits shifting as they plow through the disk, and as they grow, their gravity begins to reach across the system and shove their siblings. Computer simulations of young planetary systems show the same thing again and again. Close encounters, gravitational slingshots. A giant planet sweeps past a smaller world, and the smaller world is flung, its orbit stretched or bent or broken entirely. Sometimes the victim is hurled into the star, and sometimes it is thrown outward faster than the system's gravity can ever call it back. It leaves. It simply leaves forever, carrying whatever it was born with, its rock and ice, and perhaps its atmosphere, out into interstellar space. Some astronomers suspect our own solar system may have done this in its youth, that we may once have had another giant planet, a fifth sibling for Jupiter, Saturn, Uranus, and Neptune, that was ejected during the early chaos. If so, somewhere in the galaxy tonight, an exile from our own family is drifting in the dark, and it has been falling through emptiness for 4 billion years. Before we talk about how we find them, stay with the ejection itself for a moment, because if the planet had a surface and an atmosphere and weather, the process would be the strangest apocalypse imaginable. Not fire, not impact, just departure. From the surface of a world being thrown out of its system, the catastrophe would look at first like almost nothing. The sun rises and sets as always, but month by month it rises smaller. The days grow imperceptibly dimmer, the summers fail, the oceans, if there are oceans, skin over with ice that never melts again. The sun shrinks from a disk to a brilliant point, from a point to merely the brightest star in the sky, and then, over years, to just another star among thousands, and then to nothing anyone could pick out at all. The atmosphere cools until its gases begin to condense. Rain of oxygen, then snow of nitrogen, the sky itself gently settling onto the ground as frost. And then the world is finished changing, sealed, complete, a museum of itself, and it simply continues, outbound, into a night that will never end. No explosion, no violence you could point to. The quietest way a world can be lost. Finding such worlds sounds impossible, and it very nearly is. A rogue planet emits almost no light. It reflects nothing because there is nothing nearby to reflect. It transits no star, tugs no star into wobbling. Every technique that found the 6,000 worlds of our catalogue fails completely. except one, and it is the most elegant trick in all of astronomy. Einstein taught us that mass bends space itself, and that light follows those bends. If a rogue planet drifting through the foreground of the sky happens to pass almost exactly between Earth and some distant background star, the planet's gravity acts as a lens. It focuses the star's light, and for a brief window, that background star appears to brighten, swelling and fading in a smooth, telltale curve. The planet itself is never seen, only its gravity is seen, a fingerprint of pure mass sliding across the light of a star far behind it. The alignment has to be nearly perfect, and it happens by pure chance, and it never repeats. A given rogue planet will cross in front of a given star exactly once in the lifetime of the universe. Astronomers call it gravitational microlensing, and to use it, survey telescopes stare at fields of millions of stars for years on end, waiting for the universe to wink. The universe winks more often than anyone expected. A survey called MOA, Microlensing Observations in Astrophysics, spent 9 years watching the dense star fields toward the center of our galaxy from an observatory in New Zealand. When researchers led by Takahiro Sumi at Osaka University analyzed those 9 years of data, published in 2023, they found something remarkable. The brief, sharp lensing events, the ones caused by planet-sized masses rather than stars, were far more common than the older models predicted. Extrapolated across the galaxy, their results suggested that free-floating planets, most of them small, rocky worlds, could outnumber the stars of the Milky Way by a factor of roughly 20. The Milky Way holds at least 100 billion stars. Run the multiplication and the conclusion lands somewhere hard to absorb. There may be trillions of rogue planets in our galaxy alone. Now, honesty requires the caveat, and it matters. These extrapolations lean on a small number of detections, fewer than 10 strong candidates for low-mass rogue worlds so far, and other careful studies come out far lower, closer to 1 free-floating planet per star. The true number is genuinely uncertain, and a new space observatory, NASA's Nancy Grace Roman Space Telescope, is expected to settle much of the question, with predictions that it alone could detect hundreds of Earth-mass rogue worlds. But notice the range of the argument. The pessimistic estimate is 100 billion sunless planets in our galaxy. The optimistic one is trillions. Either way, the conclusion stands. The galaxy's starless worlds are not exceptions. They may be the majority of all planets that exist, which would mean the most common kind of planet in the universe is a kind our solar system cannot show us, a kind no one has ever seen up close. The dark ones. The wanderers. If you want evidence that objects really do travel between the stars, that the space between systems is not empty but trafficked, the universe recently delivered it to our doorstep. In 2017, astronomers spotted something crossing our own solar system on a path no solar system object could follow, moving too fast to be bound by the sun's gravity, an interstellar visitor. It was named Oumuamua, a Hawaiian word suggesting a messenger or scout arriving from far away, and it passed through, swung around our sun, and departed forever, the first confirmed object from another star system ever observed inside ours. 2 years later, a second visitor came through, an unmistakable comet from another star called Borisov. 2 interstellar travelers in 2 years through one small solar system implies that the galaxy is absolutely awash in wandering material, from pebbles to comets to, inevitably, planets. And the James Webb Space Telescope has added its own puzzle. Surveying the Orion Nebula, one of the great stellar nurseries, astronomers identified dozens of candidate objects with planet-scale masses drifting free, some of them apparently traveling in pairs, orbiting each other with no star anywhere near them. The finding is genuinely disputed. Other teams argue some of these may be misidentified background objects, and the argument is still live in the scientific literature. But the fact that we are seriously debating whether the Orion Nebula contains free-floating pairs of Jupiter mass worlds tells you how far we've come from the tidy universe where planets knew their place. So let's visit one of the wanderers properly. Choose any patch of the sky between the stars, because statistically, they are everywhere, and fall toward one of those small rocky worlds adrift in the black. What would it actually be like? Descend toward the surface, and the first thing you notice is that descent means nothing here. There is no dawn side, no dusk side, no equator worth the name. Every direction is midnight. The surface, if we light it with our imagination, is a landscape of rock and ice, mountains and plains and frozen seas of gas, sculpted long ago when this world still had a sun, preserved now at temperatures approaching absolute zero if the planet is bare. The sky above is the finest sky in the universe. No sun ever washes it out. No atmosphere may remain to blur it. The Milky Way arches overhead in permanent crystalline glory, hundreds of billions of stars, none of them yours. If the planet still has a moon, and simulations suggest some ejected planets do keep their moons through the catastrophe, then a black companion crosses the starfield in silence, an absence moving over the absence. Nothing else happens. Nothing has happened for billions of years. This is what most of the galaxy's real estate may actually look like. Not fire, not glass storms, just cold rock under beautiful stars, unlit, unnamed, uncounted. And yet, here is the twist that has fascinated scientists for decades, ever since the planetary scientist David Stevenson raised the possibility in the late 1990s. A rogue planet's surface is dead by any measure we know. But a planet does not get all of its heat from its star. Planets carry their own warmth, deep inside, heat left over from their formation and generated continuously by the decay of radioactive elements in their rock. Earth's interior right now is hotter than the surface of the sun, entirely on its own merits. Normally that internal heat leaks away into space, a trickle beneath the flood of sunlight. But suppose a rogue planet is wrapped in insulation, a thick global shell of ice, kilometers deep, or in Stevenson's boldest version, a dense primordial atmosphere of hydrogen retained from birth, blanketing the world so effectively that the interior heat cannot escape. Under that insulation, the temperature climbs, and calculations show it can climb past the melting point of water, which means that beneath the frozen crust of a starless, sunless, permanently dark, wandering planet, there could be oceans. Liquid water oceans held warm for billions of years by nothing but the planet's own radioactive heartbeat, in perfect darkness, unfrozen and stable, while the world drifts between the stars. We already know from the moons of our own outer solar system that buried oceans are real and common. Europa and Enceladus almost certainly have them. A rogue planet ocean would be the same idea, cut loose entirely. No one is claiming there is life in such places. But when scientists list the settings in the galaxy where liquid water could persist, the Wanderers are on the list. Life's most basic requirement, possibly satisfied on worlds with no sun at all. If that were ever true, even once, then somewhere out there in the eternal dark between the stars, there is an ocean that has never seen light and never missed it. Here is a thought to file under things that sound like science fiction, but are simply statistics. If the larger estimates are anywhere near correct, if the Wanderers truly outnumber the stars many times over, then the nearest planet to Earth, outside our own solar system, is probably not orbiting Proxima Centauri or any other star. It is probably a rogue, some dark, quiet world, drifting through the space between us and the nearest stars, closer than any alien sun, completely invisible to every instrument we currently possess. It could be out there right now, well inside the distance to Proxima, a whole world with mountains and ice and perhaps a deep buried ocean passing silently by while we search the stars beyond it. We would have no idea. The galaxy's largest population of planets is also its most perfectly hidden, and the closest stranger may be nearer than we have ever thought to look. There is one more thing to say about the rogue planets, and it is the quiet one. Nothing bad is happening to them. Sit with that for a second, because after everything we've seen tonight, it matters. The glass rain world is being scoured. The lava world is boiling. WASP 12b is being eaten alive by its own star. The Wanderers suffer none of this. No radiation strips them. No tide stretches them. No star will ever swell into a red giant and swallow them. They are, in a strange sense, the safest planets in the universe, beyond the reach of every catastrophe that stars inflict, wanting nothing, losing nothing, keeping their oceans, if they have them, on a time scale that will outlast every sun in the sky. When the stars of the Milky Way have burned out, trillions of years from now, the Wanderers will still be there, unchanged, still falling through the dark on their long, patient orbits around a galaxy gone quiet. The universe's most terrifying planets may also be its most peaceful. It simply depends on whether you fear the dark or the fire. We have traveled a long way tonight, glass rain and a world of perfect black, a lava sea with a breathing sky, iron falling in the dark. A planet with the temperature of a star, a planet shaped like an egg falling into its sun, a planet on a comet's path, a world with two sunsets, planets orbiting a corpse and planets orbiting nothing at all. Each of them is real. Each of them is out there right now, doing everything I've described in complete indifference to whether anyone is watching. And now it's time to ask the question that has been waiting underneath this entire journey. If this is what planets are actually like, what exactly is ours? Step back with me now, away from the individual worlds, and look at the whole catalogue at once. More than 6,200 confirmed planets in more than 4,700 systems, with thousands of candidates still waiting in line. 30 years ago, the number was 0. This is one of the fastest transformations in the history of science, a complete census of a kind of object that, within living memory, was pure speculation. And a census tells you things that no single discovery can. It tells you what is normal. When astronomers step back and read the statistics of 6,000 worlds, the numbers rearrange everything we thought we understood about our own place in the universe in 3 ways. 2 of them are wonderful, 1 of them is deeply strange. And remember how fast this all happened, because the speed is part of the wonder. In 1990, the confirmed count of planets beyond our solar system was 0, and respectable astronomers could still publicly doubt whether such planets were common at all. In 1992, the pulsar planets made it 3. In 1995, 51 Pegasi b opened the floodgates for ordinary stars. By 2009, when Kepler launched, the count stood in the hundreds. Kepler alone pushed it into the thousands. And this year, the tally passed 6,200, with the pace still accelerating. A single human lifetime, not even a long one, spans the entire history of this science. There are astronomers working today who began their careers when humanity knew of no planets beyond our suns, and who may end them studying the atmospheres of Earth-sized worlds for signs of life. No generation before ours ever got to watch a question this old, "Are there other worlds?" collapse into an answer this fast. Here is the first. Planets are everywhere. In the early years, every discovery was a lottery win, and it was still possible to believe that planetary systems might be rare, that our sun's family might be some kind of fortunate exception. The statistics have destroyed that idea completely. When you correct for all the planets our method still cannot see, the small ones, the distant ones, the ones whose orbits never cross their star from our point of view, the numbers indicate that planets outnumber stars in our galaxy. On average, every star you have ever seen carries at least 1 world. Walk outside on a clear night, look at any random star above your roof, any one at all, and the smart bet, the statistically responsible bet, is that something is circling it. Planets are not the exception in the universe. They are the default. The Milky Way is not a collection of stars with occasional planets. It is a field of hundreds of billions of planetary systems, and every point of light in your night sky is best understood as somebody's sun. And the variety among those worlds goes so far beyond tonight's itinerary that I want you to understand something clearly. The planets we visited were not the complete list of wonders. They were a sample. We passed over a world called WASP 107b, about 200 light-years away, a planet with roughly the mass of Neptune puffed up to nearly the size of Jupiter, so wispy and low in density that astronomers describe it, in all seriousness, as a cotton candy planet. When the James Webb Space Telescope examined its skies in 2023, it found water vapor, sulfur dioxide, and clouds made of silicate sand. Sand lofted high into the atmosphere by turbulence, forming clouds that rain their grains back down into the hot depths, where they vaporize and rise to form clouds again. A complete weather cycle made of sand. We passed over HAT P7b about 1,000 light-years away, where observations suggest the clouds may be made of corundum, the mineral that forms rubies and sapphires, gemstone dust sweeping from the night side into the day on winds that make the planet's weather visibly change from one year to the next. Sand clouds, gem clouds, glass rain, iron rain. Every time we point our instruments at a new world, the universe seems mildly offended that we thought we had seen everything and shows us a new kind of sky. Here is the second. The most common kind of planet in the galaxy is a kind we have never once seen up close. When you sort the catalogue by size, the single most abundant category of world sites in the size range between Earth and Neptune. Astronomers call them super-Earths or sub-Neptunes, depending on where they fall, and the galaxy manufactures them in extraordinary numbers, around star after star after star. There they are, worlds of 2 Earth masses, 4, 8, some probably rocky and huge, some wrapped in deep hydrogen skies, some perhaps covered in global oceans hundreds of kilometers deep. And now, look at our solar system. Count our worlds. We have small rocky planets, and we have giants. We have nothing in between. Not one. The most common planet in the universe is precisely the one our system forgot to build. Think about what that means. For all of human history, we assumed our solar system was the template, and the question was how closely other systems would match it. The census inverted the question. Our system is the odd one. The universe's ordinary everyday planet is something no probe of ours has ever photographed, and every child in every classroom on Earth grows up learning a planetary lineup that is, galactically speaking, eccentric. And the strangeness of our home system doesn't stop there. Hot Jupiters, the scorched giants that dominated tonight's journey, orbit only about 1% of Sun-like stars, and we don't have one, blessedly, because a hot Jupiter is not born beside its star. A giant planet cannot form in that furnace. It must form far out in the cold, and then migrate inward, and a giant planet migrating through a planetary system is a wrecking ball, scattering and swallowing the small rocky worlds in its path. Somewhere in the histories of all those hot Jupiter systems, there may be a graveyard of destroyed Earths. Our Jupiter, by contrast, stayed in the outer dark on its wide, calm, nearly circular orbit, where its gravity may actually shield the inner worlds, deflecting some of the comets and debris that would otherwise rain inward. Our giant behaved. Many giants, the catalogue shows us, do not. The orbits in the catalogue are wilder too. We've seen eccentric paths like HD 80606b's comet plunge, worlds on polar orbits, worlds orbiting backwards relative to their star's spin, systems packed so tightly that 5 planets crowd into orbits smaller than Mercury's. Against all of this, the solar system's serene, well-spaced, nearly circular architecture looks less like the rule and more like a stroke of luck. But the census gives with the other hand, and here is where the story turns hopeful. Because in all that data, astronomers have also learned how common the ingredients of a world like ours might be. Small, rocky planets are abundant, and some of them orbit in the region scientists call the habitable zone, the band of distances around a star where the temperature allows liquid water to exist on a planet's surface. Not too close, or the water boils away. Not too far, or it freezes solid. Just there, in the middle, in what some call the Goldilocks zone. When researchers ran the statistics from the Kepler mission's survey, the estimates that emerged were staggering. Rocky planets in the habitable zones of their stars are not rare. Depending on the assumptions, our galaxy alone could hold hundreds of millions, perhaps billions of them. Billions of worlds at the right distance, at the right size, where rain, real rain, ordinary water rain, could in principle fall on rock the way it falls on your street. Some of them are almost unbearably close. In 2016, astronomers confirmed a small planet orbiting Proxima Centauri, the nearest star to our Sun, just over 4 light-years away. It is at least about the mass of Earth, and it sits in its little red star's habitable zone. The very nearest star to us has a potentially rocky world at the right distance for liquid water. And 40 light-years away, around a dim red dwarf called TRAPPIST-1, astronomers in 2017 announced one of the most extraordinary systems ever found. 7 planets, all of them roughly Earth-sized, all 7 orbiting a star just 8% the mass of our Sun, several of them in or near the habitable zone. 7 Earth-sized worlds around one quiet ember of a star, huddled so close together that from the surface of any one of them, the others would hang in the sky as visible disks near neighbors, the way our moon hangs over us. If you stood on one of the TRAPPIST-1 worlds at night, you would see other Earth-sized planets above you, showing phases like moons, close enough that crossing to them would be a journey of days rather than lifetimes. The galaxy has built places like that, places that make our loneliest dreams of company look modest. Honesty asks for a caveat here, and it's an important one. Most of those tantalizing nearby worlds, Proxima's planet, the TRAPPIST-1-7, orbit red dwarf stars, and red dwarfs are complicated hosts. They are the most common stars in the galaxy by far. Small, cool, and almost immortal, but many of them, especially in their youth, are violently temperamental lashing their close-in planets with flares and radiation that may strip atmospheres entirely. And because a red dwarf is so dim, its habitable zone hugs the star so tightly that any planet within it is probably tidally locked, one face in permanent day, the other in permanent night. A condition tonight's journey has taught you to treat with suspicion. Whether a tidally locked red dwarf world can hold its atmosphere, circulate its warmth, and keep oceans on its day side is one of the great open questions in astronomy right now, and telescopes like Webb are attacking it, system by system, planet by planet. The honest answer is that we don't yet know whether the galaxy's most common stars can host living worlds. The universe has not made this easy for us. It rarely does. So planets are everywhere, and rocky worlds at comfortable distances number in the millions or billions. Now comes the third finding, the strange one. The one that has been hiding underneath this entire night. With all of that abundance, with more than 6,000 confirmed worlds and 30 years of relentless searching, we have still not confirmed a single true twin of Earth. Not one. Understand exactly what I mean by that, because it's a precise claim. We have found planets the size of Earth. We have found planets in habitable zones. We have found planets the size of Earth in habitable zones, and some of them may be magnificent. But a planet the size of Earth in the habitable zone around a calm yellow star like our Sun, confirmed to have oceans of liquid water on its surface, an atmosphere we could breathe, a surface where you could stand unprotected under a warm sky. That planet is not in the catalogue. Partly, this is a limitation of our instruments, and it's worth feeling the sheer difficulty of the problem. When Earth passes in front of the Sun, as seen from some distant vantage point, it blocks less than 1/100% of the Sun's light, a dimming of roughly 1 part in 10,000, and it does so just once a year for a matter of hours. To confirm the pattern, you'd need to catch that whisper of a dip several years in a row, without blinking, without confusion from the star's own flickers and spots. And the gravitational tug Earth exerts on the Sun moves our enormous star at just about 9 centimeters per second, slower than a garden snail's determined crawl, a wobble our best instruments are only now becoming sensitive enough to distinguish from the Sun's own restless churning. An Earth twin around a Sun-like star is close to the hardest possible thing for our current methods to detect, and it is entirely possible, many astronomers would say probable, that such worlds exist in great numbers just below our threshold of vision. The next generation of observatories is being designed in large part to find exactly them. But the fact remains, and it deserves to be said plainly. We have searched 6,000 worlds, and we have not yet found home. The blue, mild, water-soaked, oxygen-skied kind of planet you are lying on right now is, as far as direct human knowledge extends, unique. There is exactly one confirmed specimen in the universe. You're on it. Now, as we finally approach the end of our journey, I want to bring you back to the question I asked at the very beginning of tonight, the one hiding inside the title itself. What are the most terrifying planets ever discovered? We've toured the candidates, the world where glass flies sideways on supersonic winds, the world so black it swallows its own existence, the lava sea, the iron rain, the planet with a star's own temperature tearing its molecules apart, the egg-shaped world falling into its sun, the comet planet burning and freezing on a 111-day heartbeat, the ghost worlds of a dead star, and the trillion silent wanderers with no star at all. Any of them would be a defensible answer, but I don't think any of them is the true one. Because terrifying, if we're honest about the word, means something that threatens what we love. And nothing on those worlds threatens anything. There is nothing there to lose. No forest burns on WASP 76b. No harbour drowns on 55 Cancri E. The iron rain falls on no one, and has fallen on no one for billions of years. Those planets are not tragedies, they are just weather, in the dark, without witnesses. The most quietly terrifying discovery in the whole catalogue, I'd suggest, is the statistical one. It's the empty column in the census. 6,000 worlds and no confirmed second Earth. The terrifying planet isn't out there at all. It's the one we haven't found. It's the silence in the data where home should be. But turn that thought over, gently, and it becomes something else entirely. Because you can read the same fact in two directions. One direction says, "We are alone until proven otherwise," and that's frightening. The other direction says, "Look at what you have. Look at what you are lying on." Tonight, we crossed hundreds of light years, and everywhere we went we found variations on fire and darkness and poison, and then we came back to a world where the rain is water, where the sky is a soft, breathable ocean of nitrogen and oxygen, held at almost exactly the right pressure, at almost exactly the right temperature by a magnetic field that quietly turns away the solar wind while you sleep. Where the sun is a stable, patient, middle-aged star that hasn't significantly betrayed its planets in 4.5 billion years, where the giant planets stayed in the outer system like a guardian instead of ploughing inward like a wrecking ball, where the orbit stayed circular, where the oceans stayed liquid, where, at this exact moment, the most extreme weather event within 40 light-years of you, as far as we can confirm, may well be a thunderstorm somewhere over the Pacific. Every world we visited tonight was a lottery ticket, the universe scratched and lost. You live on the one that won. And here's the part I find genuinely moving, the thought I'd like to leave tucked under your pillow. We only know any of this because somebody looked. Think about the chain of quiet, patient, stubborn human effort behind tonight's journey. Somebody spent years timing the flickers of a dead star's radio pulse and refused to ignore a wobble smaller than a millisecond. Somebody pointed a telescope at 100,000 stars for a decade, waiting for dips in brightness of less than 1%. Somebody worked out how to read the color of a planet's sunset from 60 light-years away, how to catch iron vapor crossing a distant terminator, how to weigh a world using nothing but the stretch of starlight. None of those discoveries fed anyone. None of them made the discoverers rich. They were driven by the oldest and most humble human instinct there is, the one you feel as a child the first time you really see the night sky, the need to know what's up there. They looked, and the universe answered. They looked, and impossible worlds became real places with names. They looked, and the storms of planets we will never visit became part of the story we tell our children. That's the spirit that carried us across 6,000 worlds in 30 years. And that's the spirit that will, sooner or later, and perhaps sooner than we think, find the second pale blue dot and end the great silence in the census. Because the search is not over, it is barely beginning. The telescopes that found everything you heard tonight are already being outclassed by their successors. New observatories in space and on mountaintops are being built for one explicit purpose: to find and study small, temperate, rocky worlds around calm stars, to photograph them directly, to read their atmospheres, to look for water, for oxygen, for the unmistakable chemical fingerprints of life. The children being born this year may grow up in the generation that finds the first true twin of Earth. They may know its name the way you know the names of the planets of our own system. And when that world is found, everything we saw tonight will take its proper place in the story, not as a catalogue of horrors, but as the long list of everything a planet can be, against which we finally understood the one thing a planet so rarely is: gentle. And if any of tonight stays with you, let it change one small thing. The next time you find yourself outside on a clear night, try something. Look up, and instead of seeing points of light, practice seeing what you now know is actually there. That star is somebody's sun. So is that one. So is that one. Around them, statistically, almost certainly, worlds. Perhaps a lava world, perhaps a wanderer's abandoned family, perhaps something no one has imagined yet. If you're in the northern hemisphere in the late winter or spring, you can even find the constellation Cancer, faint and unassuming between the bright stars of Gemini and Leo, and somewhere in it, if your sky is dark enough, the dim star Copernicus, the one your own eyes can just barely catch, 41 light years away, and in orbit around it, the lava world Janssen, its glowing ocean rolling on at this very moment, its 18-hour years ticking past several times while you sleep tonight. You don't need a telescope to be an explorer anymore. You only need to know what you're looking at. The night sky has quietly become a map of real places, and you are one of the first generations of human beings who has ever been able to read it that way. So here is where our journey leaves us. Tonight, while you sleep, the glass will fly sideways through the blue skies of HD 1897333b, exactly as it did last night. Exactly as it will tomorrow. Tonight, while you sleep, the black world will make another silent third of its orbit, swallowing the light of its star. Tonight, while you sleep, the lava ocean of Janssen will roll on under its steaming mineral sky, and the iron rain will fall through the darkness of WASP 76b, and Kelt 9b will pass through 2 entire summers and 1 winter before your alarm goes off. Tonight, while you sleep, WASP 12b will spiral 12 hours closer to the end of its story, and the two suns of Kepler 16b will move a little further through their slow waltz, and the three ghost worlds of the pulsar will keep their perfect time around their impossible clock. And tonight, while you sleep, the wanderers, all of them, the billions or trillions of sunless worlds, will fall onward through the dark between the stars, carrying their frozen mountains and just possibly their warm, hidden oceans further into the quiet. None of it stops. None of it ever stops. The universe runs all night, every night, and it asks nothing of you at all. You are allowed to just rest here on the calm one and let it all continue without you. Thank you for joining me tonight on this journey through the strangest and most terrifying planets ever discovered. If this exploration moved you, challenged you, or made you look at the night sky a little differently, please take a moment to like this video and subscribe. It genuinely helps this channel continue these deep journeys through the cosmos, and it helps other curious minds find their way here too. And if you're still awake, drifting somewhere between the iron rain and the sand clouds, let me offer you one last image to carry into sleep. 64 light-years away, the glass storms of that beautiful blue planet are raging right now, exactly as they have for billions of years. 1,000 light-years away, gemstone dust is drifting across a night side no eye has ever seen. And between the stars, beyond counting, the dark wanderers are falling through the silence, calm and cold and endless. None of it needs you. None of it will ever notice you. The universe's most extreme worlds will go on doing extraordinary things indifferently forever. But here on the rarest planet we have ever confirmed to exist, the night is mild, the rain is only water, and the ground beneath you has held every sleeper who ever lived. The strangest planet ever discovered is the one holding you right now. Sleep well on it. Good night.